Okay, well, I'll keep this kind of sweet because I know I'm the one that's getting in the way between your breaks. So, this discussion is actually about hierarchical services through a WAN backbone, a packet backbone, which I call a network service provider. And what this enables is, while I talk about Ethernet MANs, it doesn't necessarily have to be an Ethernet. It's for any upstream to downstream kind of service, where the upstream provides a hierarchical kind of scheme of MPLS services to the downstream, which allows the downstream then to use that upstream for both transit services as well as hierarchical MPLS services. And I make the relationship to Ethernet MANs because the biggest problem we have right now in the Ethernet, in MANs, especially Ethernet, is this ability to use a backbone, which I'll define. So the problem we got in Ethernet services or downstream is trying to get to multiple cities is basically how do you deliver economical services between cities. And so the first problem you get is, do you operate your own WAN network, global network, whatever you call it, and your metro network, and try to make all that operate? And being a greenfield, that's even much more tougher. And so that's really complex and costly. The other alternative then is to just go buy traditional private line services like Lambdas, ATMs, Sonnet, and that is a possibility, but the problem is that there's still a lot of complexity involved. It's an overlay model, and as you'll see, the problem with any of the traditional telecom services, it's distance sensitive. So if I want to operate and drop off cities all over North America and then finally Europe and Asia, it's going to cost me a lot to deploy this on any traditional telco circuit. So the next kind of thing you want to do is you want to look at this and say, well, what can I do? Well, the first thing is that the IP backbones, they're great because they're distance insensitive. So the first thing is if I can get an IP fabric to deliver lots of capacity and gives me a good kind of quality of service or service, and it's distance insensitive, I'm only paying for the price of how I plug into that backbone and use that backbone, which is kind of nice. The other one is if I can push the complexity of operating a global WAN backbone to NSP partners by using some scheme which I'll talk about, it also reduces my cost of operational cost. To do this, we want to make sure that whatever services we do within the city looks the same to other cities, and there's no real restrictions of going within the city or across the city. And the last thing is we want to make sure we can deliver some SLAs within the city to other cities using NSP backbone, and want to make sure that there's some certain SLA characteristics that the service looks the same whether it's in the city or across to different cities. So the first question is, we could certainly use an IP backbone and use, for example, various tunneling techniques, IPsec, GRE, also a Martini kind of tunnel. We can also use Carides L2 VPN kind of solution. And that certainly will work, which means we get the access to the IP backbone and we can get VPNs on it. But the problem we get then is there's an operational cost. It's the old N square problem. Right now I have 3 cities. I bring in the 4th city and I have to provision the border routers in every one of those I'll call EMANs or Ethernet MANs. I got to provision them with layer 3 kind of topology information. So what happens is I'm still running a virtual backbone. And so what I'm presenting in here is the ability of doing something similar where I can use the packet backbone but do it through a peering model, just like 2547. So what I'm really presenting is a peering model, 2547 carrier-to-carrier extensions, but I'm going to articulate this a little bit better than section 9 of the draft. So in the overlay model, you can see you get an N-square kind of problem of meshes that I have to, or the operators of this MAN has to kind of worry about at every border, which is an issue when you run from the 49th city and go to the 50th. So what we try to do is the peering model, 2547 or VPRNs, what it offers is the ability to do this peering concept where the network, the upstream networks, looks like a big gigantic router. So in this case, we have 3 cities, and when we bring the 4th city, the NSP just kind of advertises that 4th city, and all the other cities get access to that new city coming online, and there's no configuration changes. So this is very powerful, that as I roll out new cities and use the upstream's backbone, it looks as an extension to my services, and I don't have to go modify any of these border routers are between the man provider, the downstream, and the upstream. And another thing you can look at in the presentation is that the LSPs going to these mans are really managed and operated by the upstream. They're actually, as the city comes online, it actually just shows up in all the other cities, as you can see. It's not something that the man provider has to provision on all of his border routers. So how do we do this is the question. So what we get is this kind of model where everything is just, you know, opaque to the man provider, and it's a peering relationship. So the first part is, in the peering model, what we get is we get an NSP that runs his traditional network. It's a packet-based network, probably running MPLS, and he offers this intercity man service or a downstream hierarchical kind of service. And then on every city, what I call the man 1 and man 2, we have a function of a border router, of a AS boundary router that's peering with the PEs in the NSP. Also, what's really important is the mans, man 1 and 2, are running their own IGP, but they're on the same autonomy. So what the model looks like is this, is that you get, in the blue is the NSP. The blue NSP has its own traffic engineered links, which is the bottom blue kind of traffic engineered LSP, the NSPT LSP. Then the next one above that is what we call the intercity LSP. Now this LSP is really operated by the NSP, and it's delivered out to every city in the VPN of this man provider. So in this case, let's say Terrabeam is the man provider, and we have city 1 and city 2, man 1 and 2. The NSP's responsibility is, as I bring up cities, to deploy and deliver that intercity LSP to all the other cities in an automated fashion. This means I don't have to provision anything, and everything is automated. And this is highly important, since because at the AS boundary functions, I have all my flows going through that for my transit services and all my other intercity traffic, that any operator mistakes can be devastating. So there's an operational issue on when I can do this if I didn't have this kind of model. Now once somehow we automate this function where this intercity LSP, the FA-like kind of LSP is done, then the man provider or downstream can have free access to put as many LSPs as he wants to put on it, or send IP traffic on it. So what we get now is the effects of a VPN and a transit kind of service, peering kind of service for traditional IP, all in the same interface, and it's hierarchical in nature. And the really important thing is that second LSP there, you call intercity LSP, it's FA-like. It actually forms the adjacency between CE1 and CE2, not at PE1 and PE2. And that's very important because all state information and all adjacencies for LDP and RSP state information is not on the PE provider's box, which means he can support, you know, hundreds and thousands of downstreams and not having problems with scaling issues. So when I presented this presentation in July to the Metro Ethernet Forum, I also had Yakov work with me on this, and he helped me refine this, and we came up with this idea of exactly how to do this. So one of the things, before I get to the exact details how to do this, we also important is to get the class of service mappings from all the higher service LSPs down all the way through the intercity LSP and also to the traffic engineer LSP. So that maintains the class of service, and we all know how to do this, just EXP markings and pass them down. So the proposal is to join RFC 2547 BIS, which was well defined on a carrier to enterprise relationship, and very loosely defined on how to do carrier-to-carrier relationships. And I think 2547 is a great model for exactly this, for carrier-to-carrier. And the reason is the routing tables from an enterprise, you know, they're not what I call aggregated. And any kind of omission of any routes will be pointed back to the NSP to figure out, you know, what's going on, which means a horrendous operational issue. On a carrier-to-carrier model, the downstream is really highly aggregated routes. So it fits in really well. So what I'm proposing here is we take RSC 3107, which is BGP MPLS, and you mix it with 2547, you get exactly what I just described above. So how it works is like this, and I'll go into actual details. And again, you have the NSP in blue and the MAN providers in yellow, and that represents two different cities. So the first thing that happens is that the NSP would probably create a traffic engineered link between PE1 and PE2, and this is very important that he either does it through LVP or RSVP. He has to create a traffic engineered link or some kind of tunnel or between PE1 and PE2, part of the 2547 BIS spec. And that allows reachability from an IGP point of view between PE1 and PE2. So I won't get into that, that's in the spec. So basically, the NSP just deploys 2547 on his network, in the middle of his network, and the next thing that happens after he's created the adjacency between PE1 and PE2, the CE1 ASBR announces prefix 1. So in this case, ASMAN1 announces prefix 1, but instead of announcing just prefix 1 with BGP, he also announces an MPLS label. Now, instead of running just giving any label, you can use an implicit label, an implicit null label. And that implicit null label then gets mapped to, with the prefix, the PE1 takes the prefix and the label, and he appends to it a route distinguisher so that it's now recognized as a VPN IPv4 route, and he assigns a route target, which gives it the VPN membership, and the BGP next hop becomes PE1, and the label L, the null label, is now assigned label L, which is used for egress targeted port on the way back, which we'll see. That then gets announced all the way through his network to all his other networks, and finally gets to PE2, where city man number 2 is. And what happens then is PE2 announces that reachability information to CE2 and says, man ASBR, AS1 has come up prefix 1, and I'm announcing it to CE2, and I'm going to assign, in this case, label K, because it got swapped as part of the function. So L got swapped to K. And this time the BGP next hop is PE2. So when this is done, what you now get is the blue on the top. You've got an LSP that has been formed, that has been created by this interaction of BGP MPLS and 2547. And what this happens now is you've got control information flowing between the MAN provider and a peering model to the upstream back to a MAN provider, and you get a hierarchy on the top flow. And then you can put anything into this, and what happens is when you put like regular IP traffic into it, you push in regular IP, you push in label K, K gets remapped to L at PE1, at PE2. L then looks and says, okay, I got PE1 from my BGP next hop, resolve to IGP, push on label swap, I just call it label swap. Gets to PE1, PE1 pops it again, he pops L, and then finally he looks at the packet and there's a no label packet, and so he pops it out to CE1 and the packet flows. So you just had a regular IP packet. For an LSP to go across, and this is a cross between MAN 1 and 2, an LSP like an RSVP would be sent, for example, a path message, and this, what happens is it's very important that the path message, the hop object gets pushed with the IP address of CE2 as the input to the tunnel. So what has to happen is this hierarchical LSP has to behave like an FA-like forwarded adjacency-like characteristics. It has to make sure that the P-hop is set correctly for RSVP to work. And this could be used for LDP or RSVP. What happens eventually is you get an inverted tree happening from all the multi-points to the point. And this is the data flow, the direction of the data flow, which means now you can pass hierarchical services or just IP services over it. And if you then do it bidirectionally, you get this kind of multi-point or rooted tree, so you get C1, C3 to CE2, and so on. And then what you get is an inverted tree that's bidirectional in nature, and it'll deliver you hierarchical services. So the issues involved is how do you get this class of service model, which I talked about, to give you end-to-end signaling for call admission control, so you get a hard QoS model. And to date, no NSP can deliver a jitter service or guarantees on jitters. So these are the two issues that still need to be worked on. This proposal is being submitted into the IETF in the next month from myself, Yakov, and probably 9 or 10 other authors, which is still getting kind of finalized. So I hope everybody got that. It's kind of a little complicated and confusing, but anyways. Any questions? Okay, thanks.